This is Statistical Rethinking, second edition, chapter 14, and we're on the final easy question, 14E3. Okay, so the question is, when is it possible for varying slopes to have fewer effective parameters, as estimated by WAIC or PSIS, or you could even throw in cross-validation here. Then the corresponding model with fixed unpooled slopes. That says that. It should say then. Give me just a second here. Okay, so let me read that one more time. So when is it possible for varying slopes to have fewer effective parameters than the corresponding model with fixed slopes? Explain. Okay. This is my answer for it, and it's just a lot of text, and so I will try to paraphrase here. Okay. So the first thing to recognize is that the effective number of parameters is the penalty term for these different estimates. Okay, WAIC, PSIS, or cross-validation. Okay, and so roughly speaking, the more parameters that are used to fit a model, the larger the penalty. Okay, and this should make sense because in general, the more parameters that are being used to fit a model, the more flexible that model is. And the more flexible that model is, there is a greater risk of overfitting to your current data and therefore not generalizing to other data that you might wish your model to generalize to. Okay. So now, just as a little bit of a detour, there's a way that I sometimes like to think about penalty and complexity and the complexity of models that really isn't presented in the book, but for me it's a useful little heuristic, but that the penalty term is proportional to the volume of prior space divided by the volume of posterior space. And so by the volume of prior space, I mean all of the possibilities that your model can entertain before seeing the data as a prior, divided by all of the possibilities that your model entertains after seeing the data, after being trained on the data. Okay, and so if you kind of think your way through this, if you have a very flexible model, you will have a high volume of prior space, and just because of the nature of having many parameters, when you train it on data, it will shrink. That space will shrink around very tightly to your data in the posterior space. Okay, and so then your posterior space will be very small. So if you have a large prior space and a small posterior space, that indicates a greater probability or more a greater likelihood of overfitting. Okay, so you can kind of think your way through that a little bit. So anyway, kind of getting back on track now. Let's directly go to the question. So right away we should suspect that using varying slopes will have more effective parameters than fixed slopes, right? And the idea is fairly simple. In fixed slopes, one slope is one slope, but for varying slopes, we will have a different estimate for each level in the data. And so by level we mean a cluster or a panel or whatever. So automatically it's clear that we're making more estimations with varying slopes than we are with fixed slopes. And so we should assume that fixed slopes are going to have fewer parameters. Okay. And as a first level passover, that does make a lot of sense, but we need to get a little bit more nuanced. So when we are estimating the effective number of parameters, or the penalty term, with WAIC or PSIS or cross-validation, we're not actually going through and counting parameters, right? We're not saying one parameter, two parameters, three parameters. Instead, what we're doing is we're trying to quantify the flexibility of the model, okay? And then we're calling that an effective parameter, or we're translating that to the scale of effective parameters. Okay, so we can have these situations where we have a single parameter, okay, Now, a single parameter with a more permissive prior distribution is going to lend that model more flexibility than if it had a tighter prior distribution. Okay, so here we see that one parameter can have different numbers of effective parameters. Okay, because of how tight the prior is will lead to different flexibility in the model, and more flexibility means more effective parameters. Okay. So now that we have that idea, we can run with this and then recognize that if we have varying slopes and they are organized hierarchically, right? So we're saying that all of these slopes are coming from one kind of master distribution. Well, in that situation, the priors for each of the slopes, of the varying slopes, are being estimated using information from the other panels, from the other clusters. And so then it's possible for the prior, the prior that is being constructed from this hierarchical structure to become smaller and therefore lend less flexibility to the model than a single parameter that has sufficiently, voluminous prior distribution. Okay, so I hope that makes sense. And I hope that by reading this, it makes sense. If it doesn't, please leave a comment, and maybe I will do some simulations to kind of demonstrate this. That's just a lot of work, and I hope that this idea is intuitive enough. So anyway, we'll call that good.